Hellman Key Exchange using an intuition with colors. Right? Computers, of course, cannot understand colors, so we need to convert this entire system into something more mathematical, something more computer understandable. Right? And that's what we're going to do in this video. We're going to convert Diffie Hellman Key Exchange color-based analogy into something more concrete and something more mathematical. So the two properties that we saw in the last video was A operated on B. You should not be able to deconstruct A and B even if one of A or B. That was property number one. Property number two was given A operated on B operated on C should be exactly equal to A operated on C operated on B. Right? So notice that we've swapped these two values over here. And this did hold true, right? In the color example, we saw that once the colors have been mixed, they cannot be unmixed, which implied this assumption. The second thing is if colors are mixed in any order, it does not really matter. So you mix yellow plus green plus blue, or you do yellow plus blue plus green, they're exactly the same. Okay, so which satisfies this equation as well. So the colors definitely satisfy these two properties, but what is a mathematical function that satisfies the same two properties? Let's look at that. Let's say A operated on B is A to the power B. Let's look at the second property first. A operated on B operated on C is equal to A to the power B whole to the power C, and operated on C operated on B is equals to A power C whole power B, right? So A power B whole power C is equals to A to the power of B times C, and this is equal to A to the power C times B, and both of these are exactly equal to A power BC. So the second property definitely holds, but does the first property hold? If I do A to the power B, and if I give you A, you can deduce B by saying log of A power B is equals to B. So the first property does not hold. The first property in which given A operated on B, which is A power B, and if I give you A, I can construct B by just taking a log to the base A. Right? So that is why we have to make a small change over here such that A operated on B is A to the power B, but modulo a large prime number P. Right? So modulo P basically implies when you divide the value by P, what is the remainder? And this is hard to reconstruct. If I give you the value of A, you'll still not be able to deduce the value B if it has been already moduloed with a prime number P. Right. So this is something that I want you to trust me on before we proceed. So this is the equivalent of mixing colors. So in the mixing colors, we made an assumption. The assumption was if two colors are mixed, they cannot be unmixed. And this is a similar kind of quote-unquote assumption that we're going to make. That is A to the power B modulo P is unmixable. That is, even if I tell you the value of A, you cannot deconstruct the value of B. So this is an assumption that we're going to run with. Okay, so now let us look at doing the Diffie Hellman Key Exchange using the mathematical terms that we just looked at. We'll take an example to put it into practice, right? So the operation that we've defined so far is if A is operated on B, we get A to the power B modulo P for some prime number P. So let's just pick a prime number, let's say 487. Right? In practice, the prime numbers are really large, 20 to 30 digits long, but for simplicity's sake, I'm going to pick a relatively small prime number. Okay, so now let's define the operator itself. Given A and B, it returns A to the power B modulo P. Right? So this is just the Python syntax of the same thing. Okay, what was the first thing that we did in the colors example was we picked a generator G, right? In that example, it was the color yellow that we picked as the generator. Here we are going to pick a number, a prime number, which is 289. And this is now going to be known to everybody. So let's take note of who knows what. So this is me, this is the messenger, and this is you, right? So I know G is equal to 289. The messenger knows G is equal to 289, and G is equal to 289. Right? So everybody knows what the generator is. It's public information. The first thing that I then do is pick a private number for myself, which is 41. In the colors example, this is the color green that I had selected. right? So what we have over here is, notice nobody else knows this private number 41. So what I need to send to you is a public version of me, which is the mixture of the two colors. So in the colors example again, I took the color yellow, took the color green, mixed them, and then send that to you. That's what we're going to do over here. We're going to operate the generator on the private key that I selected, right? And so what that means is all of us know the public key that I'm sending out, which is 439, right? And all of us have this information. Cool. So what are you going to do? You are going to select a private number for yourself, let's say 229, and you're going to generate a mixture. You're going to mix these colors again, which is, and you're going to send public you to everybody. Cool. So now everybody knows the generator, the public me, public you, right? Now the shared secret that I am going to generate is going to be a mixture of what you sent me with my private key, right? So let's just call this shared secret me. And what you are going to generate is the operation of mixing the public key that I sent you, that's public me, and the private you, that is the private key that you had selected, right? And these two should be exactly the same, right? So both of them are 394. So what both of us have is shared secret me, that is equals to 3. Note that the messenger does not have this information. So this is shared you is equals to 394, but the messenger does not have the shared secret. So both you and me have arrived at the shared secret, which are exactly the same. And now we can start encrypting the data using this shared key. Okay, so now the messenger has access to G, public me, and public you. And none of this is the number 394. Is there some operation that the messenger can do so as to generate the number 394 deterministically? The answer is no. Let's try mixing public me and public you, right? Let's say this shared secret guess. So if the messenger tries to mix the public keys that I sent to you and the one that you sent to me and just mixes that together, as we noticed in the colors example, would get a slightly different result. In the colors example, we saw that the color that the messenger would end up with is a slightly more yellow version of the secret key that was shared. And in this case, you can see that the color that, or the number that the messenger can generate is only the number 433, which is not equal to the actual shared secret, which is 390. So this is a quick example to show you that you can do the Diffie Hellman key exchange using numbers, and this is something that a computer can do. A computer cannot, of course, talk in colors, but it can talk in numbers. So we have established a way for computers to establish an encrypted channel between you and me over the internet. Awesome. So in the next video, we will look at how Diffie-Hellman key exchange is actually used on the internet in HTTPS. So yeah, see you in the next video.